Beneath the forests and rugged coastline of the Pacific Northwest, something enormous is happening. Nothing, and that is exactly what worries scientists. Stretching offshore from Northern California to Vancouver Island lies one of the most powerful fault systems on Earth, a section so quiet it has not ruptured in more than 3 centuries. Seismologists call this stretch a seismic gap, not because it is empty, but because it is silent. And in earthquake science, silence can be the loudest warning of all. The Earth's tectonic plates never stop moving. They shift slowly, sometimes just a few centimeters each year. But over decades and centuries, that motion adds up. Along many faults, this constant movement releases tension in small, frequent earthquakes. The rocks grind past each other, relieving stress bit by bit, but not here. In certain places, friction wins. The plates press together and lock tight. The boundary stops sliding, even though the forces pushing it never stop. The crust begins to bend. It flexes. It stores energy like a giant compressed spring. This process is known as elastic rebound. As the plates attempt to move, the locked fault resists. The surrounding rock deforms slowly, invisibly, accumulating strain year after year. Deep underground, rough patches of rock called asperities grip each other with immense force. These jagged zones can hold for generations, but nothing holds forever. When the stress finally exceeds the fault's strength, the grip fails, and the energy that has been building for centuries releases in seconds. Laboratory experiments help explain why some faults creep quietly while others stay locked. When rock samples are subjected to stress, they show 2 distinct behaviors. Some exhibit velocity strengthening friction, movement increases resistance, preventing sudden rupture. Others show velocity weakening friction. Once motion begins, resistance drops rapidly, allowing catastrophic slip. The most dangerous faults are dominated by velocity weakening friction. They do not slip gently, they break. Not all strain builds silently. In some subduction zones, scientists observe slow slip events, movements that unfold over days or weeks instead of seconds. These are often accompanied by faint seismic signals known as episodic tremor and slip, or ETS. They are like whispers from the deep, but they rarely relieve the heart of a locked zone. The core remains stuck, preserving the potential for something far larger. To measure this tension, scientists track something called slip rate deficit. This is the difference between how fast the plates are trying to move and how much motion is actually being released. If the plates are converging at 4 centimeters per year, but only a fraction of that is being released through small quakes or slow slip, the remainder builds as stored energy. In the Pacific Northwest, that deficit has been accumulating since the year 1700. 300 years of silence, 300 years of strain. This is the physics that turns calm coastlines into sources of scientific unease. A quiet fault is not a peaceful fault. It may simply be waiting, and nowhere is that waiting more profound than along the Cascadia subduction zone. The locked off the coast of Oregon, Washington, and British Columbia. A massive tectonic boundary stretches more than 1,000 kilometers. It is known as the Cascadia subduction zone, where the Juan de Fuca plate slides beneath North America. Modern GPS stations anchored in bedrock across the Pacific Northwest tell a remarkable story. The coastline itself is slowly being compressed, inching eastward by about 4 centimeters each year, but the fault offshore is not sliding. It is locked. Satellite radar technology, known as INSAR, confirms what the GPS data reveals. The crust is bending like a flexed ruler. The energy is building. Since the last known great earthquake in 1700, scientists estimate that more than 15 meters of potential slip may have accumulated. 15 meters. That is not a minor adjustment, that is a continent-scale release waiting to happen. The memory of the last rupture survives in both science and story. In coastal marshes, researchers have discovered layers of sand buried beneath peat, evidence of a massive tsunami. Radiocarbon dating points to the winter of 1700. Across the Pacific, Japanese historical records describe an orphan tsunami, waves arriving without a local earthquake. The timing matches perfectly. Indigenous oral histories along the Pacific Northwest coast tell of a night when the ground shook violently and the ocean swallowed villages. One Huayot account recalls, the land shook, the ocean rose up and covered everything. Science and story agree. Cascadia has done this before. Today the gap remains locked. Monitoring networks run continuously. Hundreds of sensors track minute movements. Strain meters buried deep in boreholes. Seismographs listening for tremor. Satellites scanning the core of producing a magnitude 9 earthquake shows little change. Statistical models estimate roughly a 10 to 14% chance of a magnitude 8.5 or greater earthquake in the next 50 years. But probability is not prediction. It could happen tomorrow. It could happen decades from now. The only certainty is that the stress continues to accumulate. Cascadia is not dormant. It is charging. Lessons from Chile and history provide sobering examples of what long silence can mean. In May 1960, southern Chile experienced the largest earthquake ever recorded, magnitude 9.5. For centuries before that event, the Valdivia segment of the subduction zone had been quiet, too quiet. The Nazca Plate had continued pressing beneath South America, building a massive slip deficit, more than 20 meters. When the rupture came, it lasted nearly 10 minutes. Entire cities were destroyed. A tsunami crossed the Pacific, striking Hawaii and Japan. The lesson was clear: silence is not safety. Half a century later, northeastern Japan faced a similar reality. The Tohoku region had long been considered a seismic gap. The last comparable event dated back to 869 AD. Few expected the scale of what occurred in March 2011. A magnitude 9.0 earthquake tore through the Japan Trench. The seafloor shifted by as much much as 50 meters in places. The tsunami overwhelmed seawalls, devastated towns, and triggered the Fukushima nuclear disaster. Afterward, scientists realized the fault had stored far more strain than previously believed. Both Chile and Japan shattered the assumption that long, quiet segments release energy gradually. Instead, they proved that centuries of stored stress can release in one catastrophic rupture. These events haunt every locked fault being monitored today, especially Cascadia, the limits of prediction. In earthquake science, prediction remains elusive. Seismologists can measure strain, they can calculate probabilities, they can map stress transfer between fault segments, but they cannot name the day. The Parkfield segment of California's San Andreas Fault once seemed predictable. Magnitude 6 earthquakes had occurred roughly every 22 years. Scientists installed dense instrumentation in the 1980s, expecting the next quake between 1988 and 1993. It didn't arrive until 2004. Nature ignored the schedule. Today, hundreds of sensors blanket the Pacific Northwest, yet vast stretches of Cascadia lie offshore, beyond dense monitoring. Slow slip signals may occur unnoticed. Early rupture signals might begin beneath the ocean floor, hidden from view. Instead of precise forecasts, scientists rely on probability models. They estimate risk over decades, not days. As USGS seismologist Lucy Jones has said, we can see the pressure building, but we cannot say when it will break. More than 3 million people live above this silent boundary. Cities like Seattle, Portland, and Vancouver thrive along its edge. Life continues normally. The ground feels solid, but deep below, strain is accumulating inch by inch. The silence is not reassurance. It is a question. Cascadia has broken before. It will break again. The only uncertainty is when. Science cannot promise warning. It can only offer preparation, because when locked faults finally move, they do not whisper, they roar.